Hello, dear students. My name is Andriy Semenets. I am Associated Professor of Medical Informatics Department, and today I will provide for you materials of the second lecture of Medical Informatics and Biostatistics course with topic regarding Introduction to Medical Analysis and Processing. Topics is significantly broad, and it's very difficult in one lecture to really cover all this question. So practically I will try to provide some backgrounds about place of imaging in medical science in general, then cover questions which is related to most closely related to aim of lecture about acquisition, analysis and processing of medical images, at least on some basic level, and then we'll present some brief introduction about picture human communication system and format for medical information exchange, Gcom 2. Let's proceed with first question of lecture. So it's important to understand that medical imaging is a multidisciplinary field and also identify proper place of medical imaging in modern medical science, as well as approach for image analysis, modalities or classification of type of medical images, and kinds of information that could be retrieved by medical images, at least classics class. So imaging be seen as an essential aspect of medical science for visualization of anatomical structures and functional or metabolic information of the human body. Actually, for hundreds of years, it's like only drawing and painting being used for this with manual processing. And so such kind of information important for understanding anatomy, physiological process, function of organs, behavior of whole or part of organ under influence of abnormal physiological condition or diseases. With last century, a little bit more than last century, about 120 years, development of imaging instruments has been inspiring evolution of new computerized image reconstruction, processing and analysis method for better understanding and interpretation of medical images. And recently, intelligent and model-based quantitative image analysis approach have been explored for computer-aided diagnosis to improve and sensitivity and specialty of radiological tests involving medical images. So medical, as I said, medical images in diagnostic radiology is evolved as a result of significant contribution of number of different disciplines from basic science, engineering, medicine, and for sure at first place we must put physics, which actually give us our technical capabilities to perform recording of medical images and to perform ability to look inside the human body with non-invasive with minimal invasive methods. So within recent years, with about 40-50 years, numbers of computer vision methods have been developed for variety application in image processing, segmentation, analysis, and recognition. So however, computerized image reconstruction, processing, and analysis methods have been developed for medical image application, and they are required specialized knowledge of specific medical imaging modalities that's used to acquire of image. And as I mentioned before, that medical informatics is multidisciplinary fields, and we need collaborate with different scientific area with aim to develop a new approach for medical image visualization and analysis. So every time we will be based on current understanding of physiology and anatomy, and need to identify physical principles, and only physics give for us methodologies to new methods, new approaches to retrieve medical images, and not only medical images, imagine in general. So we need to identify, discover that physical principles. Then we need to apply engineering, computer science in order to develop instruments that will utilize that specific physical principles. Like, I mean, already used X-ray or MRI or gamma radiation or other methods. So we need to develop instruments with utilize newly discovered methods, or explore advances in already existing physical methods. So, and final result of this instrument, of working with this instrument, will be typically electrical signal, which will represent of information, represent of visual information from about physiology or anatomy of patient. And in modern time, it's best way to digitize this information and start with computer processing, analysis and modeling of it in digital form. So it's give for us information and knowledge for creating diagnosis, for create treatment plan, perform some apply to patient, and we come to new level of understanding of current understanding of physiology and anatomy, and loop will be repeated again and again. So radiological science in the last 4 decades right now have witnessed revolutionary progress in medical imaging and computerized medical image processing. And major advances in multidimensional medical image processing involve various applications of X-ray imaging, like not only conventional X-ray scan, but various usage of different type of computer tomographies, mammographies, and other similar system. Also application of nuclear medicine system like single proton emission tomography, positron emission tomography, ultrasound, usage of modern ultrasound system with capabilities up to visualize dynamical models. Also usage of magnetic resonance imaging as well as functional version to visualize different physiological principles. So, as regarding of modalities or approaches to classify of medical imaging principles, very multiply approaches available, and one of this it will be usage type of energy. It's modalities by type of energy which is used to retrieve of image. Practically, we can identify 3 types of sources of energy: internal, external, and combination. And we have multiply representatives for each of these sources. And maybe even would be better to visualize this not with the text script, but with the following diagram, which cover even more cases than previous slide, and shown that only single positron emission tomography practically as representation of nuclear medicine device use only internal energy source for visualize of human body, like emission of nucleus, radioactive materials. Other use of external illumination to retrieve reflected or transilluminated medical image, or combination of both. So most common cases for external energy, it's various types of X-rays visualization, conventional radiography, mammography, tomography, and other systems. Ultrasound system, transillumination, and optical transmission transillumination imaging. With combinational source being used different kinds of MRI systems, of fluorescence imaging, electrical impedance imaging systems, and several others, even like SPECT from nuclear medicine too. Okay. So another approach of consider modalities and the medical image, it's use physical characteristics. Like here is 3 type of modalities presented within this slide: wavelength, frequency, and energy, because they are tightly related. And here is actually every time we have placed particular types of medical image processing at this, which is related to specific wavelengths, frequency, and energies. And here is shown where can be identified MRI, X-ray, gamma ray, image, medical imaging. And with general aim, what we should do with visualization of medical images, it's like transform information which represent data, transform data from Z ranges, wavelengths, frequencies that could not be observed by our sense, could not be identified by our senses, and turn that in that narrow part of electromagnetic radiation spectrum that we can sense of it by our eyes, and it's accessible for us by our eyes. But for sure, if you talk about mathematical processing, analytical and data analysis methods, application of such methods no need that transformation. We can directly analyze information which is obtained from specific method of medical imaging. So, and to come too closely to the first question, if you talk about type of information, as I already mentioned several times, it could be anatomical or metabolic information, or combination of both, for example, as in case of ultrasound, which is good for provide both kinds of information. But some other methods very specific only to provide only anatomical information, like all kinds of X-ray visualization, including computer tomography, or much better to functional and metabolic information like functional MRI and so on. So now major part of lecture, second question, which cover the multiply aspects of image acquisition, analysis, and processing. So first of all, we need to identify image, conventional biomedical image processing analysis system, then check what is digital image in general, so it provide definition of digital image and how we can deal with it. To spend some time to check physical principles of transmissional imaging, and then again I will back to methods for overview of methods for analysis and processing. So if we consider any medical diagnostic equipment, modern diagnostic equipment, which is dedicated to create medical image, so it will be consist of usually 3 parts. First of all, it will be image acquisition subsystem, which major aim is convert of biomedical signal or radiation carrying the information of interest to a digital signal, practically to electrical signal, which is absolutely most case in modern time is digitized and represented in form of digital data. Then general computer unit could be used for purposes like, first of all, store this information and perform advanced processing option, even prepare that digital sequence, digital data sequence to be visualized with built-in display, built-in or separate display unit, or provide networking services and so on. So we can have multiply features, multiply function dedicated for DC unit. Even if you talk about specific mobile solution like portable ultrasound machine, and so on. All these three components still will be our labels, and just maybe built in almost in one case, in one represented as one unit. So now time to perform like actually quick recap and check our understanding what is image in general. So if we talk about any kind of physical images that could be stored from starting from painting, drawing, so I am not talking even about digital format. We can consider or that things that we could sense by our eyes. We can consider image as, especially flat image, as two-dimensional signal or multi-dimensional signal if we will talk about volumetric images or so. So most common situation when we work with medical image, for sure it will be different flat images. It's in the past it was only drawing and painting. Right now it's typically various types of photos or printed images or so on. So we talk about two-dimensional images and we talk about two-dimensional signals where X and Y direction represent coordinate of a single element of picture or pixel, and actually at this intersection X and Y coordinate we have some specific continuous function which represent characteristics of picture element at this specific point. I talk about continuous because we can, depending to our number of value along X and Y axis, we can change size of picture element. We consider smaller or larger part of our flat image. So it's probably will be not a single characteristic at intersection, but multiply characteristics. Right now I'm talking about continuous or so-called analog image. For sure, in case of if we will try to replace continuous with some digital representation, we will have at intersection only that's finite value of something. So from here it's objective that things that vital characteristics of any image, it will be dimension or picture size or picture resolution, number of X and Y coordinates, number of picture elements along X and Y coordinates, and it could be typically not corresponded for physical dimension, which could be typically measured in meters and millimeters, centimeters, and so on. Also, if you want to come to description of what is in fact dynamical image or like video sequence of so, it's changes sequential, it's sequence of series of flat two-dimensional image. We change it through time with given frequency. So here as we introduce third axis time, and we have still deal with sequence of two-dimensional signals which form our dynamical signals. And similar way we can try to introduce three-dimensional signal instead of time. Coordinate we will use depth or z, or even four-dimensional when we still add the time as fourth dimension. For sure, a function or continuous value of picture element, as I said, it's multiply time. If we talk about continuous element, it's represented as continuous signal, and it could represent characteristics of image. For example, it could be grayscale image when we talk about some levels of gray, or it could be, in case of color image, it could be intensiveness of each color component for this specific picture element. So most of the time, we must identify flat two-dimensional image as two-dimensional signal. In general case, it's continuous. Each pixel element have continuous value f from xy. For sure, when we talk about conversion, creating of digital image from this any real continuous two-dimensional image, we need to switch from, we need to perform registration of this image, and for this we need sensor which will convert some energy levels, no matter which represents some frequency, wavelength, also into electrical signals. Fine example, it's even a camera in our smartphones or camera which translate to you my video from my room for this lecture. So all this device used not single sensor but array of sensor, and when we need to create digital image, we need some set of sensor, and each sensor element will be responsible to create single to perform registration of single picture element and convert into digital representation information about each one single picture element. So in this particular case, on this chart, you can see how it could be performed. When we have any scene elements that we want to visualize it and retrieve digital representation of this element, it needs to be illuminated by external energy source. It could be sunlight, or it could be even another kind of source, and it's not necessary to be reflected light. It could be transilluminated line in case if we talk about X-ray imaging, but idea will be the same. We illuminate scene element and we register reflected image, reflected energy or transilluminated energy, or we perform focusing by using imaging system. It could be optical components, or it could be some magnetic coils, for example, or so on. It's, for example, I'm talking about MRI images, and so energy source illuminated onto internal image plane, and so reflected side fell onto sensor array and being registered by sensor. And here is important point that when we talk about creating a digital image, so first demand is to have a sensor array of that size of sensor array must be enough to produce digital image with required quality. And so here is we have like two cases, and left side what is fall onto digital sensor array, and at right side what is the response generated by this digital sensor array and sent to for further processing to, for example, digital computer unit. And it's exactly the same thing. It's no matter what we're talking about. Is it we're talking about digital X-ray imaging, or is it we're talking about taking photo with smartphone camera, or taking selfie with smartphone, and so on. So principle exactly the same. If it doesn't have enough number of digital sensor, if our pixel is too large, final result will be not not enough accurate, not enough precise, and will be very hard to use this information to perform some, for example, medical diagnostics based on it. So how look like digital image if we have too low number of pixels, too large picture element? We have like some not very significantly useful number of squares of different colors. And if you will enlarge any digital image with enough magnificent level, you will every time come to this situation. And it's the reason why cameras in modern smartphone have 12, 16, 20 megapixel, 20 millions of sensors to create picture with enough quality. And it's even much more significant in case of medical imaging. So finally, when we talk about formation of digital image, we talk about replacement of matrix, where which element, which cell represents some continuous signal about specific picture element with its digital representation with discrete value. We have continuous function as input, and we perform approximation of this function to some closest digital number and place it. And finally, we have all our digital image. It will be matrix of pixel, where each element represents pixel characteristics. So it's the reason why still until now, digital image sometimes called matrix images. And in case of practical example, how it can look like for medical image, when we have analog at the left, it's the top, and we enlarge small part, which is selected here by red, we enlarge it, we enlarge our sensor array, and we will see how sensors being illuminated. In this case, at left bottom, so at right top represent process of how analog signal being converted into digital equivalent, simplification, and final outcome for this small area. Final outcome is matrix, which represent in this case information about grayscale image, and we have intensiveness of gray in which cell which reflect our analog image. So for sure, if we talk about full color image, it will be not single value, but it will have multiply value per each color component. For example, if we use RGB color palette, it will be 3 values for red, green, blue components of color. And as should be obvious consequence, if we talk about any image, even to visualize digital image, we must be able to, or our computer system, digital computer unit, must be able to manage with this numerical data set and convert it back into a visual representation in form of visual representation like this one at left bottom object. Now about relationship between physical principles and medical images that could be obtained within this way. So a little bit about transmission imaging, how we can have its work, and what kind of medical image could be retrieved in this way. So I'm talking about only acquisition of medical image, only method of acquisition. And here is given list. So major basic principles of medical imaging to transmission, it's radiation estimate when passed through a human body. And here is general methods for retrieving image. Basic include X-ray X-ray imaging, infrared, optical, microwave, and similar. So actually, actual revolution with medical imaging start from discovering of X-rays, which is confirmed by priority by patent by Conrad and Hahn, but need to remember that in those years not only Mr. Hahn but other scientists work on similar tasks, and even Ukrainian scientist Ivan Poluy achieved same results, but Mr. Hahn have priority in his achievement by documental priority, and he earned a Nobel Prize in Physics. So again, we are talking about discovering, not inventing, that all that physical principles works in nature for million years before, but just human scientist, human professional does not have equipment to register, to discover and register this. So since end of 19th century, it's become possible, and it has been started to using in medical purpose. So main idea, beam of X-rays directed toward patient and recorded from the beginning by film, which is sensitive to this wavelength, to this frequency, but right now film replaced by digital sensor array, which works exactly the same. So how X-ray radiography working, and modern system which use digital array, and we can immediately, let's say, image X-ray image in digital format. So what is for us interesting, it's not conventional X-ray imaging. That's actually, for sure, if we get digital image, we can perform then some further processing, filtration measures, and etc., etc. So it will be 15 minutes later. But most interesting for us, it's computer tomography. Its ability to perform advanced visualization based on some physical equipment, some X-ray sources, and maybe a bit more advanced detector when we need which allow for us to, let's say, image not from not in direction of observation, but in perpendicular direction. So here, as you can see, what kind of information will be transmitted and received by detector, and what actually will be finally visualized with computer screen printed on film or even paper. We have information from consection. We have information which is look like we look from 90-degree angle compared to focal place of visualization. So in general tomography, its graphic representation could slice and implies a formation of two-dimensional cross-section image free of blurring from structures not in place of interest or tomograph. So I means I scan in horizontal direction, but I, let's say, image if I would look in vertical direction into a place where I perform scanning. And computer tomography is the formation of tomograph of X-ray absorption coefficient by methods of reconstruction from recorded projection. So we record in multiply projection and we perform reconstruction from here. Actually, this achievement was done in end of 1960 by two computer and physics experts, and they earned a Nobel Prize in medicine at end of 1970s for their invention. I mean CT scan machine. So they perform recording of multiply projection by under different angles by rotation sensor and sources and detectors around human body, and they develop methodology which allow to reconstruct original image from this information. So, and we got approach to ability to create first of all two-dimensional and further even three-dimensional anatomical visualization of human body. And here is major difference between X-ray imaging and computer tomography as well, even basic computer tomography, which at the beginning of age of development, when we perform observation of scene with X-ray, we got direct projection, and when we perform analysis by using computer subsystem, we have ability to reconstruct image in perpendicular direction. So from this from XY area, like if you look inside along Z-axis into here. And what is make possible this achievement? So what is general way into, first of all, two-dimensional tomography, but three-dimensional imaging actually, and then even three-dimensional tomography. So first of all, like here is its critical points. We need achievements. First of all, physics, discovery in physics, X-ray imaging, end of 19th century. Then second step, critical, it's mathematical results, mathematical achievement, especially so-called radon transformation. We need also Fourier transformation, but radon transformation is critical. And even in time of First World War, so this methodology was developed, and at those time it doesn't have practical application, and it's not considered possibility of usage in medicine of it. But with time passed, 50 years later, it's become scientists assume that given methodology could be applied for processing of digitized part of medical image, and we have chance to reconstruct synthetic image and retrieve much more information. So we get computer tomography. Now, very quickly, I pass through some mathematical assumptions. It's actually very advanced mathematical principles lie behind computer tomography. And okay, that's anyway, it's need to be at least aware about existence of it. And what is important point that despite I will talk about more transmission X-ray tomography, but same principles, same mathematical methodology, same computer science implementation of mathematical algorithm has been used not only for X-ray computer tomography, but MRI and fMRI and nuclear computer tomography like SPECT and PET, and even to modern ultrasound system. So we talk about, we talk about that we have significant difference in physical principles of retrieving of information about patient anatomy, physiology, but from mathematical perspective, from computer science viewpoint, there is no significant difference between once we digitize that input signal, we could apply almost exactly the same methodologies to reconstruct our final image. So here is in chart given principles of how obtain information, how measure the integration of human body from first generation of computer tomography. Right now it's much more advanced, and now a little bit mathematic. So especially radon transformation. So what it gives for us? Linear transformation, which allow for us to retrieve that G from S theta function, which in same way provide a relationship between attenuation of energy inside scene element, not only human body, and intensiveness of signals that we register at end. So here is we have this double integral, and here is we have this solution, which give for us this colored one, the signal transformation, radon transformation. And for sure it's important to have as much possible more measures It's give for us more information and results will be more precise, but directly radon transformation, results of radon transformation are almost useless. If we will perform scanning of that phantom element at right side, and if we would try to visualize information on CVRP radon transformation for digitized data obtained from scan, it would be something like this one at the center. Almost don't tell nothing. Magic comes at next step when we will invert radon transformation. And inversion of it gives chance to retrieve original representation of origin or original image or image of original object. So, and here is it's allow for us recover inner structure from projection. And so what is useful, it's two-dimensional continuous signal and usage of two-dimensional Fourier transformation, which is rotationally invariant. So here is actually really advanced in mathematics required to understand how this processing, and even it's not goal for you, but at least you must know about existence of it. So we use rotational invariant features of two-dimensional Fourier transformation, and here is we will create relationship if we have this relationship between original radon transformation data and similarity in this one-dimensional Fourier transformation. So two-dimensional Fourier transformation give for us reconstruction of original function. So like we have similarity for one Fourier transformation between G and G capital, similar way, we can assume that we have similarity between f from xy and their Fourier representative since after two-dimensional Fourier transformation. So, and if you will revert this bottom part, we got original scene from these things. Here is it's covered projection theorem. So again, it's very complex mathematics, and even me, as I'm not mathematician, it's very hard to even understand basic about this. And here is given statement of projection theorem. Practically, not any one physician, no need right now to manually implement it and even understand this solution. Everything already done. We have algorithm, we have computer software which already work it. But we just need to know about the existence of it and about role which give for us projection theorem into reconstruction of our original image. So if we will fill it out in block structure, we can denote the following process like this one. We provide as input our radon transformation data, then perform single Fourier transformation, come to full Fourier space, perform double Fourier reverse transformation, and we got to origin. For sure, in reality, every time we have some interpolation, we are not working with exact precise values. So every time we have some delta X and Y errors in our results. And this reason, when we talk about computer tomography image, we must be every time aware that it's not a real representation. Every time we talk about synthetic content, synthetic image with some level of errors which is already included in visual structure. Backward point. So we are talking about single one point at how to get correct coordinates for single one point of digital image that will represent our computer tomography projection. And given operation must be perform, so given function must be perform multiply time, so calculation of Radon transformation and reversing of it by this pair of integrals, and 3 integrals in total, for each point in our data which is retrieved during computer tomography. So we are talking about huge data processing and huge computational resources required to perform this analysis. And we have it since 1960 of 20th century. And what it will have, it's like this. We have, for sure, it's squares, it's a three-dimensional object, their Radon representation at the center, and results of reconstruction depending on number of projections that we have. So more number of projection, more accurate results we will retrieve in this case. In case of application in medicine, we got this one. We got ability to retrieve computer tomography image, and here is it's about the beginning at the end of 20th century, and even better images we have right now. But it's important to note that modern tomograph have a resolution much less than camera in your smartphone, and it's significant things because it's much more difficultly to register attenuated energy by via X-ray digital sensor than optical light by smartphone cameras. So modern tomograph, computer tomograph does not have moving parts, and it significantly reduces time to scan to a fraction of seconds only, and it's working in exact this manner when we have digital array of sensor. It's like half arc cover of patient body, and we have target ring that's it's illuminated by some sequence of beam of energy with using diffraction coil, and we have object recorded under different angles. Modern tomograph move forward and not only perform single local scan, but only perform continuous scanning with spiral trace around human body, and it's give for us ability to reconstruct even not only flat cross section, but three-dimensional mathematical model of object. So here is I'm talking about three-dimensional mathematical model. So like from slice by slice scanning, we can get multiply sequence, multiply cross section, and multiply cross section image. With spiral volume scanning, we have ability to reconstruct for sure with some kind of interpolation or proposal of missed elements, something like true three-dimensional model. For sure, everything that you see on your screen, and I demonstrate for you, it's again resulting of projection of mathematical model onto virtual flat two-dimensional plane of screen, and we got image like this one. Pseudo three-dimensional image. Pseudo because we perform projection of three-dimensional model to two-dimensional plane projection. And with application of advanced data image analysis techniques, and I will speak in minutes on this, we can retrieve addition, even more information. We can perform filtration, we can perform extraction of a part of images, and so on. And so what is every time critical to remember is that most closely to reality is only image like this one at left bottom corner, at left top corner, and that thinks about right bottom corner. It's fully synthetic image. It's only computer graphic reconstruction of reality, of possible reality. So if we will touch of different methods of receiving images, okay, as I mentioned, MRI, difference we have in physical principles when hydrogen, nuclear, proton under strong magnetic field spin in phase with one another and align with field, and during relaxing it's induce a measurable radio signal. We can register this, so we can convert it into digital format. As a result, we can use it as source for visualization. So method useful for visualizing soft tissue and very often used for scanning neurological studies, into studies of different pathological and of metabolical processes, and so on. So here is given different usage of approaches, like in angiography, resonance spectroscopy, and so on. So example of reconstructed angiography image, or so on. So again, what I want to say is that we have difference in physical principles, but computer parts of this tomograph are almost exactly the same as in conventional CT. Same when we are talking about nuclear medicine, when we perform measurement of distribution of radioisotope, which is distributed with body and preferable to specific organ structure of interest. And we have again useful for visualization of metabolic or functional information. So here is two different types presented. Relatively modern method of visualization. Again, we have difference in physics, we have difference in physical discovery, but there is no significant difference in principles of data processing. Similar to previous for conventional CT scan. And here is we have image of body bone densities obtained by PET. For sure, if you have multiplied different digital image obtained in different methods, and such as each one of this represented by matrix of digital numbers, so we can perform combination like addition, subtraction, and so on by using conventional mathematical approaches. And here is how we can get combined medical image. Similar way, again, when I talk about ultrasound imaging, only physical part of this device will be different, but computer subsystem will be exactly the same. Algorithms will be very similar. Just we have with only a significant problem with ultrasound imaging, that's throughput bandwidth multiply times larger than that for X-ray systems. So, and it's actually an answer why three-dimensional, four-dimensional dynamical ultrasound system just being introduced on the market at the beginning of 21st century. They required much more computer memory and computer bandwidth and CPU performance than creating even three-dimensional image by using a conventional computer tomography system. So here is how it could look like. Results. Okay. That's past 20 minutes I spent on methods and methodologies which lie behind image acquisition. Only if you want to see something on screen, how complex this mathematics and computer algorithms could be, and even I'm not sure, because it's millions of rows of codes to implement, to fully implement forward direct radon and backward Fourier transformation. But if you want to perform further processing, and we already have digitized image matrix of image data, so with this matrix we can do almost everything, and we can perform different operations regarding automatic analysis to get more advanced image, or if you will consider more detailed all these things, we have like after we perform basic enhancement, means we perform automatical adjustment to have visualization of image. We have like 3 parts what we can do with our digital data. So visualization by using convention, and that's talk about 3-dimensional visualization, like create mathematical models and visualize it on flat screen. So again, we're talking about surface reconstruction, illumination, shading, displaying. Who have played computer games, it should be known term. It's okay, for sure exact techniques. So under visualization, there I'm talking about 3-dimensional visualization, and I'm talking generation of 3-dimensional mathematical model, surface reconstruction, and visualize it on flat computer screens. So it's one direction, what we can do with our digital medical image. Second direction, right side, right hand, it's management. So create digital archives of digital data. And actually third question of lecture dedicated for this. Information system which could keep all these medical images and allow to exchange it, provide access for users. Actually, any medical diagnostic equipment already has these basic capabilities, allow to store image within computer system. It is built around it, and if you have network interface at your computer system, so you can share your data. And at the middle, as for me, most important areas of activity is automatic analysis. So identification of structures within the automatic identification of structures within given digital medical image, and which could be further used for automatic interpretation, measures, even creating diagnosis, and so on. And even we will try these examples on practicals. So a little bit more about this. Here I'm several times mentioned, and I present for you how digital image look like, matrix of picture element, matrix of characteristics of single picture, gray level for grayscale image, or 3 or more value for full color images. So if you talk about any further adjustments, like for example enlarge or reduce or magnify area of image, or maybe perform some kind of shifting scaling, it's every time will be application of matrix algebra principles. And if you perform any adjustment, any enhancement of your selfie or photo you taken by your smartphone camera, you every time use a lots of matrix algebra function, just indirect. You no need to type out this matrix function. You need to use only like visual tools in your photo editing software, different sliders, buttons, checkbox to adjust settings of your picture. But behind the scene, matrix algebra works. And here is mostly I will provide overview of these methods. So methods for preprocessing of images, like filtering, denoising, registration, enhancements. Simple case, if we talk about even converting from gray to black scale, it's approximation of gray level, and when we reduce number of gray color, and we can come from full scale gray color at left top corner to black and white and right bottom corner, when we have only 2 values, 0 and 1. Another more advanced filter, it's median, mean, wavelet, denoising, registration, and so on. In general, idea of filtering that we form new image when each picture element, each pixel of this new image depend not only depend for not only single pixel of origin image, but our neighbor around it. And here we have like conventional filters, Laplacian nonlinear filtration actually works. So for each pixel, upload specific formula with specific coordinates. And we got new image which could look like, for example, you will use this application on your practical class, but we will see a little bit in other tasks, but idea is the same. We have original image, we apply some, we select just operation, and we got results. Behind the scene, we for each single pixel has been applied complex matrix algebra function, and we got this transformation being ready. Or in other types of filtration, useful in mammography when we talk about adaptive contrast enhancement versus histogram equalization method, and so how we change original image. In other tasks, segmentation, or exactly delimitate object once they are detected. So we are looking for borders of object, like identification vessels, border of levers, and so on. And here is also will be task for you, and also you will work with visual tool, but this time application called Mavis Lab, which is again free for use like previous ImageJ, and you can check material on the Moodle topics 3 and 4 to get links to download both this application, install on your computer, and try for yourself how it all works. And here is how we can create special filter which will perform operation for delimiting tissue with different characteristics, different velocities, different characteristics, and identify parts of human brain. Then segmentation algorithm. So here is given list of names, and if you will try to search about each one of this, you will see mathematical equation which create that kind of algorithms. But again, most time you don't need to implement this directly. You need only looking for proper component, for example, that building blocks and the Mavis Lab, which each one implement, or one block implement but particular filter, or we need combine multiply block to implement that filters. Final result, that exactly things I show for you. Like we can perform filtration, we can perform segmentation, and let's say that advanced images at right side from our origin. Okay, similar way detection, we are looking for location of object of interest without prior knowledge about location existence. So it's like, in this case, we are looking about maybe pathological inclusion of some object. So here is example of identification of object which should not be in particular position, or also could be used in some kind of even automatic education and studying identification of noun object. Very useful this method when we compose synthetic image from multiple sources, like combine CT and PET image, and then possible to identify some inclusion. Here is this one, or we can identify our possible pathological changes within brain by combining MRI and PET images, or in diabetic retinopathy based on ultrasound imaging. Okay, to finalize with second step, I just want to point you to like what is considered as past, present, and future of medical imaging from like high development country science and practice. And practice, I sign. So past, it's question regarding to formation of digital image acquisition from diagnostic equipment, manipulation of pixel level, like basic enhancement, visualization, and storage. So it can be considered as already solved and nothing to do this. Present activities under practice in science and creation functional image registration of multimodal image, perform automatic segmentation, classification, measurement, so identification of object inside digital image, and then further analysis like scientific areas of activity. It's formation of multidimensional image, perform automatic computer-aided diagnostics based on results of classification, management, segmentation, and so on, then creating treatment plan and up to computer-aided surgery. Okay, possible with Da Vinci system if you have already checked fast lecture materials successfully. Okay, and now time for last question of lecture. Then I will only provide brief overview about picture recording communication system as well as Gcom. We will have separate lecture about medical information system, and I will talk then more about PACS. Right now, only essential about what is this and what is purpose of it. So we talk about PACS, picture recording communication system, like computer or networks dedicated to storage, retrieve, distribution, and presentation on image, and typically special data format has been used for this purpose, and its format is Gcom, Digital Imaging Communication Medicine standard, which describe a data format for medical images as well as even communication protocol. So aim of PACS, it's replaced hard copy-based means of managing medical images such as film archives. Instead of bunch of folders, films, and so on, we could have only digital data storage when our images are useful in digital, stored in digital format, and it's very comfortable for providing access for different physicians, for involving this for usage in data into diagnostics task, into medicine, and even if possible to apply this access for students, and we talk about usage of such data in distance education if possible. So not only this archiving features of PACS, but it's much more extensive features could be provided, and for example, it's first of all, the second major task, it's providing collaborative environment for physician and integration with other medical information system like hospital information system, electronic medical records, and so on. As of about architecture, how it could be developed, so everything will be depend to practical vendor who supply specific solution. So here is given list of different techniques which could be used, but we are not only limited with given set of technologies. Everything depends to range of system, everything depends to conventional solution. For example, even ultrasound machine being supplied together with basic PACS system, which serve information only from this ultrasound system. Computer tomography itself every time sell along with specific PACS to serve information obtained by this CT scan machine for whole hospital network that that it's working in this hospital and must provide support for it. So when we talk about usage of PACS, we talk about integration of all possible kinds of medical image into single networking system and providing access for position, creating electronic archives, and even management and analysis of images. So, and here is even more detailed listed, so we can retrieve digital images, we can interact with external information system, we can create digital archive, we can print data, provide access and remote access for physician as well as patient. How it could look like practically, multiple approaches are available. Here is given one of pair of possible clear PACS at the right side and essential PACS embedded into more general hospital information system. If we talk about digital imaging communication medicine, as I said, it's standard for handling, storing, printing, and transmission information in medical images. And it includes two components: file format definition and network communication protocol definition. So we talk about for sure application level protocol, which work above TCP/IP background, it's allow direct exchange of Gcom data set between different systems, which both capable to process Gcom data. Copyright belong to National Electrical Manufacturing Association of the United States for this standard, and so allow to integration multiply device into single network and being connected to PACs. So important features of Gcom that it's data formatted groups information into data set. So actually medical image contain not only image data sequence itself, but also contain various information like description of patient, physician, sometimes equipment, when this, where and when this image being obtained, and so on. So we have like significant metadata which describe parameters, characteristics of medical images, which is sublet inside this storage, and it provide like information about quality and reliability of our medical image, and even possible with specific solution integration or non-DICOM systems into DICOM networks. And here is available even multiply free solution, which allow for like in form of different Gcom viewer, which allow for us visualize Gcom data. Previously mentioned the ImageJ and Mavis Lab application for sure also fully support Gcom and can decode and visualize Gcom data series. Okay, that's all I want to present for you today. Thank you for your attention and have a nice weekend. Goodbye.